You know, it's just
Okay. Let's see if that stays steady. If for some reason it falls, obviously I'll let one of you guys try to pick it back up.
Well, can we catch it? Should we
Or
put something
if you-
underneath it?
You want
me
me
to
to
put my
sit
bag
behind
under
this
it?
now?
Sure, if you want.
Or I can put my bag under it if we have to.
And then I'll just grab notes from somebody in studio.
Sure.
Yeah, you try to.
Or if you want to sit there with your computer and type.
Oh, I could do that.
I mean, whichever.
Now I gotta go
I
back.
just
my
want to make
computer.
sure everyone gets the opportunity to notes. Okay.
Can you see it? You can see what it's seeing.
Because so far it would be
Hopefully it doesn't fall your
Michael
way.
and Tyler would be the ones that would need the notes. So anyway, okay. So energy flows, as Blaze said, from a hot object to cold object. So energy flows from a hot object to a cold object. And we know also, as mentioned, that what can we do with energy? Besides just let it flow, huh? We can store it. We can store it. So it can be stored. And it can be, if it flows, that means it can be transferred. Now, using a little more proper English with it, is energy a noun, you
Yes.
think?
I don't know.
It's a thing.
What?
Is it a person, place, or thing?
No,
I don't know.
thing.
Person or place.
It's a thing.
Could be a thing though.
Okay, could be.
You can't really, you can't really see it.
Can't really see it. Okay,
But it's
when you
still a
think
thing.
of, huh?
It's still a thing though.
When you think of it, what do you think of when you think of energy?
Like
What do you think?
electricity. Yeah,
Huh?
Like electricity or something.
Okay, electricity.
The little child bouncing around.
A little child bouncing around. Where does that little child get his or her energy from? Sugar?
Eating.
Adrenaline. Adrenaline.
Can of soda?
Sleeping.
Sleeping.
Yeah.
Okay.
Let's see.
So now let's stick with the idea of a can of soda or sugar. Where does that sugar or that can of soda, where did its energy come from?
Whatever the sugar comes from. I don't know.
Sugar.
The sun.
What sugar come from?
Plant. Plant. Sugar cane.
Plant. Sugar cane.
Which gets
That's
from the
one
sun.
source of sugar. Or a lot of pop that
Corn.
is made now comes from corn syrup, corn sweetener. So that came from corn. Okay? So whether it be sugar cane or whether it be corn, where did the plants get their energy from?
The sun.
The sun. Yeah, the sun.
I was right there.
Does anyone know how that works? How plants get their energy from the sun? How do they do it?
Photosynthesis.
Photosynthesis. Yeah. Anyone happen to know the part that they use to trap that sunlight?
Leaf.
Photosynthesis.
Is it in the leaves? Is it
Oh,
in
there's
the
a part on their leaves, on their petals.
of the plant.
These parts are called chloroplasts.
Oh,
The
yeah.
chloroplasts
Yeah.
trap the sunlight.
You have to translate my Latin or something.
Yeah, right. They trap the sunlight, and then they also take in, through their leaves, in the stomata, they take in CO2, and they take in water. And that CO2, that water, and the CO2, water, and sunlight all go through chemical reactions, and they create sugars, simple sugars.
Can we
That
do
the
chemical
plants,
reactions?
huh?
Like, is it possible to do the chemical reactions outside of the plants? Like, can you make sugar without it going through? Like, can you do photosynthesis without being?
Not that I'm aware of personally.
Photosynthesis.
In fact, the artificial sweeteners I know don't actually have any calories to them. I'm not sure. Not that I'm aware of. Is there such a thing as a synthetic sugar that actually has calories to it? They can make artificial sweeteners that have no calories to it, but I'm not aware of yet that they've made an actual sugar, from just artificial chemicals. Not that I'm aware of yet. Okay. So yeah, that's energy. It's created originally by plants. And then what eats the plants?
Us.
Yeah, we do some.
Animals.
Bugs.
And animals, yeah.
Bugs.
Bugs. And then what do we do with the animals that eat it?
We eat them.
We eat them, yeah.
Or they get eaten by other animals.
Or they get eaten up by other animals.
eat
And in
them.
some cases there, we eat those animals too.
Or they just die. What if they just die
What if they just
and
die?
no one eats them?
Well, they're getting eaten somewhere somehow by something.
The plants could eat the other plants.
Circle of life.
Pictures of zombies. The zombies eat the
Birds?
plants.
That circle and then go eat them.
The vultures.
Vultures, raccoons. Raccoons are scavengers.
What about like
Skunks
a
are
mushroom? The
scavengers.
mushrooms. The mushrooms.
Mushrooms are not a plant.
Fungus.
Fungi.
They're a fungi.
They're
They're the
fungi.
life of the party.
They're fungi.
They're a
real
fungi.
Yeah.
They're
That's
evil.
right.
No, but
They're
do
the life
they,
of the
wait,
party.
but the fungi eat dead things? Not
Yes.
eat them, but they, yeah. See, so mushroom could.
They help to break down and decompose
Can we eat
once
But you don't.
living
No,
things.
you don't eat mushrooms.
Anyway, okay. So the whole idea is that energy flows from one object to another, with the ultimate source of energy being
The sun.
the sun. Without the sun, we have no energy at all. So without the sun, we have zero energy whatsoever. Now, talking about the kid and sugar and food, now, we obviously get our energy from food. How do we know how much energy is in food? Ah, the calories! The calories! Does anyone know what a calorie actually is?
A unit of energy.
It is a unit of energy. It is. Protein's a little bit different. Protein, we need that. We need protein in order to break it down into what are called amino acids, which are the building blocks of protein. And then our body takes those amino acids and it remakes it because our own body has its own unique proteins in it. If I don't know if you guys did anything in middle school or not with something called DNA, but DNA is like our genetic code for all the proteins in our body. And when we eat something that has protein in it, we digest it, it breaks it down into amino acids. Our body then takes those amino acids, reassembles them in the code that we need it in order to build our muscles. That's why we need to have protein in our diets. Our muscles all the time are breaking and deteriorating, and we have to constantly repair them. That's why our body needs to have sources of protein. But no, calorie is a source of energy. And what it is the amount of energy required to raise 1 gram of water 1 degree Celsius. That is, by definition, a calorie. The amount of energy required to raise 1 gram of water 1 degree Celsius.
How much is a gram of water? Is it not much at all? Or is it
No, not much at all. In fact, I could probably get something that's
What was it
awfully close to a gram.
And then do we have a calorie to drop in there?
Let me use this
Just gotta drop. Find a little calorie cube.
One moment,
Drop in
see if
there.
I can find
Guys, we don't have the sun.
a 1 gram
What
amount.
happens? We all.
And I just did, there we go.
No one.
This is 1 gram. Feel free to take it and pass it around. That's 1 gram.
You can probably like accidentally eat it. You could.
So now you can actually say that you've been able to visualize what 1 gram feels like.
Yeah.
That is 1 gram.
What's 1 degree Celsius?
If anyone wants to put it in front of the camera just to show how small that is, feel free.
Oh my god.
I'm not sure that.
Spencer, you want to show the camera or Phil?
I want to show you.
Yeah.
It's a gram.
That's
Turn
1
it the other way.
gram.
Turn it the other way. Turn it the other way. Other way.
Okay, it's fine. It's good.
There you go.
No, no, no.
So
You had to get all sides.
Tyler and Michael, I'm sure have now had the chance to see it. Okay,
Let me see the price.
so that's 1 gram. Now, in your own mind, should it take a whole lot of energy to heat that up 1 degree Celsius? No. So a calorie is a very, very small amount of energy. Now, in all actuality, when you see something on a food label that says like 50 or 80 or 100 or 150, 200, 300 calories, that's actually, if you see like 80 calories, that's actually the unit of kilocalories. So if you see the label 80 calories, it's actually 80, kilocalories.
So they couldn't raise 1 gram of water 1 degree Celsius.
So this could literally raise, this would be 80,000 regular calories.
Oh, so it's more than just
Right.
1 Okay.
That's a lot of calories. That's a lot of pounds.
Right. So that means it could raise 80,000 grams of water a degree Celsius.
Could it raise 1 gram of water 80,000 degrees? No.
Probably. That I don't know, but that'd probably be the reverse idea, yeah. 1 gram of water, 80,000 degrees.
Pretty high.
Yeah.
Did we do? Just take a little drop.
But for us, that's what calories actually are. We use calories for our own energy need, and obviously, because it says we raise 1 gram of water 1 degree Celsius, what do you suppose that does for our body temperature? It helps to keep it going. I mean, it may obviously raise it a little, but our body also gives off heat. I mean, you walk outside right now, and you could probably see the steam coming off of you. We all give off heat. Okay? So as human beings, as we take in energy, we use it obviously for our own metabolic functions, but also to keep up our body temperature. Our body temperature needs to be at 37 degrees Celsius, aka 98.6 Fahrenheit. And if we're not, we start to see problems if we deviate too far one direction or another. If we get like 100 degrees or above, we probably start to feel a little bit sluggish. If we get cold, we don't feel right either. Okay? So our body is designed to be at that one temperature, so our body wants to be right around that. So we need to eat in order to maintain body temperature and to be able to do things with. Okay?
So if you don't eat, your temperature will go down?
Well, but your temperature won't necessarily go down because, remember, energy can be stored. So think about that. Do we have stored energy in us?
Yep.
Yeah, what's that stored energy called?
Fat.
Yeah, that's our body fat. That's our body fat. In guys, it tends to be stored more in the abdominal region. Women tends to be stored more in the buttocks and the thighs area, hip area. That's just our natural bodies. That's the way we're all built. Okay? Our bodies, male and female, do things a little bit differently because of how our functions. But our body stores that energy. Our body stores that energy. Okay. So, again, just a little bit of an FYI on this. Like I said, if you see calories on a deal, it actually means kilocalories. And the whole idea behind that is it's a lot easier of a unit to use. Kind of like how on a car, you see kilometers per hour or miles per hour instead of feet per hour. If you had feet per hour,
It'd be kind of funny if someone just like switched over to using just regular calories on like a label that said 80,000 calories. People would.
so like if we did feet per hour, 60 miles an hour would be 316,800 feet per hour.
That'd be awesome to have figured out that.
Kind of hard to put that on a speedometer. But obviously kilometers or miles per hour, a lot more of an easier number to work with. So the whole idea is they use kilocalories because it's a lot easier of a number to work with.
Instead of it being like 0 to 60, it'd be 0 to however many, like.
Right. So instead of putting like 80,000 or 80,000 for 80 calories or 300,000 for 300 calories, or let's say if the average person, they say, should have a 2,000 calorie diet. That'd be 2,000 kilocalories. That means that'd be a 2 million calorie diet. Obviously, 2 million calories, the way we're thinking of, that's way too much. But if we're talking 2,000 kilocalories, that's the right amount. But obviously, our body is mostly water. So this amount is really not a lot of energy when you think about it. It's really not. Okay? Okay. Now, in addition, so talking about these different kinds of storage accounts then. So storage accounts, which I'm on page 2, I believe here. Storage accounts, energy storage and transfer. So we've got 3 ways that we can store energy and that we can transfer it back and forth. Well, one of them is called thermal energy. That's known as ETH for a symbol. So it's ETH.
So is that just like energy and then thermal?
Yeah, thermal. In other words, basically kind of like temperature. And what does, when we have a thermometer in something, what are we measuring?
Like how much the like particles expand or whatever.
Expand and contract and
Moving.
Energy.
motion, moving, speed. Yeah.
It's right on the thing.
Okay? So this is the energy of motion, aka speed of particles. That's what thermal energy is. So that account tells you about the speed of the particles. Or I guess another fancy word for saying that would be temperature. It deals with changes in temperature. Another form of energy is what's referred to as EI. Actually, let's spell it out first. Interaction energy. So interaction energy, known as EI or EPH, deals with this idea here. I'll show you. On your temperature versus time graph, when we were doing the ice cube lab, you know, melting the ice cube, on your lab, when that straight line, did you notice something like this a little bit? Yeah. Kind of up and back and forth and back and forth, up and down. What do we say the energy from the hot plate was being used to do to the ice? To melt it, yeah. I mean, ultimately to melt it. I mean, yeah, did we see the fluctuations? Yes, but ultimately to melt it. Well, what do we know a solid looks like in terms of how the particles are arranged?
Oh, back together.
So you have a spring.
Tight together, like a spring attached. Okay? What about a liquid? What do we know about the particles of a liquid?
They kind of spread out.
No
they
spring.
Free for all.
They
Or
can
spread
go-
out.
They can
Free
float over each other.
They're free falls.
Alright.
More spread out.
Alright,
Okay.
Joshua.
Yeah.
I don't get this. If
Okay.
water melts, or not melts, if it freezes, it expands. So then how would the particles be closer together if they expand?
Isn't water like
Okay.
a fluid?
That's all nanoparticles.
Because they're close, and here's the whole idea by it. With a solid, you have a definite shape and a definite volume. Whereas if you let that same amount of water melt, what happens to all that water, like say a big huge ice cube, if I just let it melt, where does it go?
You have a definite volume.
Right, it goes all over the place. Now, when you put water, liquid water, into a container, the shape that can form is what is kind of unique about it.
What do you mean?
Okay? And obviously, depending on the container that you in, it can obviously push out one direction versus another, and that can be affected by the pressure that's inside the bottle. There's a few various other factors that can affect it.
Is water the only thing that expands when it freezes?
No.
I'm not certain.
What is it? It's on the tip of my tongue, but I can't say it.
Anyway, the whole idea is that with a
Vinegar.
solid, huh?
Vinegar.
I don't know about vinegar. I
It
honestly
does.
don't.
We had it blow up in the garage.
Oh, like in a container, you mean?
Yeah.
Okay.
Diesel does in one way though, because it gels up, so it's gonna get.
It's thicker, yeah.
So it'd be turning. It'd go from a solid. It'd go from a liquid into more of a solid kind of form, wouldn't it?
True, it does. But yeah, it all deals, it can honestly deal with the pressure that's inside the container and what direction the solid wants to form. Sometimes they might want to go up, and as they go up, they'll push upward. Okay, okay. So, anyway, so a solid closer together, a liquid more further apart. So then, we were just saying that the energy is used then to turn, it was being used to melt the solid. In other words, to turn it from a solid to a liquid. So what is the energy ultimately being used to do here? What's going on here and what's different here? What's that energy being used to do? Spread it apart, expand it. Right. Right. So this interaction energy is the energy due to attractions of particles. It can break the spring. When the energy goes into the object. Or the reverse is true. When energy is coming out of the object, it's kind of like putting these molecules back into place. It's giving them more attraction to one another. So if you're putting energy into an object, it's like taking and breaking that spring. But if you're cooling it down, it's like you're making those attractions for those particles stronger from one another. Because again, energy flows from hot to cold. So like in the case of the water and ice, it was going from the hot plate into the ice. Now, this is also referred to as phase energy. Because it can change the phase of the object. So we know we have solids, liquids, and gases. So that energy only changes when we have a phase change. Otherwise, if we have a temperature change, that would be thermal energy. If we have a phase change, then we take it out of the phase energy account. Okay, so we're just right now wanting to make sure that we're differentiating between those two accounts. Thermal energy, that account changes when the temperature changes. Interaction energy, that account changes when you have a phase change going on.
But so can like the energy change from one to the other?
Can what?
Can it change from like one to the other? The energy right?
Well, the energy itself doesn't change, it's just the account that it's coming from. Energy is energy is energy.
But so there's not like thermal energy isn't like a type of energy. Well, it's a type, but
It's
like it's not different than any other energy. It's just kind of used in a different way.
correct, yeah. It's when it's being pulled out of the when energy is being pulled out, it's kind of like, for example, having a checking account versus a savings account versus a retirement account. You know, it's like having those three different accounts. They're all money. It's all money and it's all for you. But when you pull it out is obviously different. A checking account you probably use on a daily, well, I should say a checking account you do use on a daily basis to pay bills. A savings account you probably don't use as often. You put money into it and you probably take that money out of it every so often, but you generally don't use it very much. A retirement account, you don't touch at all until you retire, generally speaking, unless you retire early.
But then you're retired, so.
So then you can't.
Or if you lose all your money in the casino, you need desperate.
Well, and then when you retire also, and I can say this knowing what my folks had to do, they took that money from their retirement accounts and then reinvested it and did like some different things with their money, put it into different funds, and there's all sorts of stuff. That's what you meet with like an investment person for, and etc.
When I retire, I'm going to take all my money and just gamble at the casino.
Yeah, right.
Either double it or lose it all and then just die. Die. If I lose it all, live in a cardboard box if I can afford that.
If you
Last
win,
one.
have a heart attack and die.
The last energy account, and we won't deal so much with this energy account. This is called chemical potential energy. Okay, chemical potential energy. Chemical potential energy. This is like taking two chemicals, putting them together, and seeing if they go boom! That kind of thing. That's chemical potential energy. It's like when you're at the gas station, they've been preaching this where when you first get gas, you want to make sure you take your nozzle and touch it on the gas pump. That way you're discharging any possible sources of static electricity, because they have found that you can have built up static electricity start a gasoline fire. And it does happen.
Would it like shoot out fire?
No, what would happen is you might take it to your car and start to pump, and then all of a sudden that touching of the metal would ignite the gasoline vapors, which could then do anything to start the pump on fire, to start your car on fire, etc. Gasoline's very, very volatile. Okay.
Blow up.
Burn the whole town down, yeah.
It's a freak gasoline fighter.
Or if some chemicals you put together and you need to heat them up to get them to react. So this is the potential for chemicals to react.
Freak gasoline.
Okay. Last thing, there's 3 ways that energy can be transferred. Energy transfer mechanisms. Heat, work, radiating. Heat would be what I'm doing right now to the room. I turn on the heater over there, and I'm letting warm particles come out of it and letting them collide with the slower moving particles in the air. That collision's like a bunch of billiard balls hitting one another. As those particles hit one another, they start moving faster, and they get the air in the room warmer. Those particles get moving faster. Working. The definition of this in science is different from the one you think of normally. You guys work. I work. Everyone works. You work by moving your hands, touching your toes, chewing, speaking, etc. The science definition of work is moving an object over a distance. And guess what? When you do that, you're using calories to do that, and you're burning energy. And then radiating is the process that the sun does when it brings UVA and UVB radiation to the earth. It hits the ground and it reflects and radiates infrared heat. I'll go back over these three things again tomorrow in a little more detail, and we'll continue. You can hit the stop button on that, please.
Yeah.
Bye-bye.